Welcome back to a new video. In this video we will discuss the part 2 of our buck converter design. In the previous part 1, we have discussed the open loop buck converter design. We have calculated necessary component values and also did some simulations in MATLAB, Simulink and also TINA to check our calculations. In this example we will look specifically at the controller, so the compensated network, and also realize that using the components in our circuit. Of course, we will do that step by step in our calculations and also verify this in MATLAB and TINA simulations. Okay, before we dive into the subject, we would like to give you the outline. Now, we have discussed in part 1 in 2 parts, the open loop calculations and also the open loop simulations. So we have done that. That is already discussed in part 1. The video link of that video is can be found in the video description of this video. Part 2 is divided in 3 parts, 2A, 2B and 2C. A will be discussing about the control theory, so in general what is a time response, the frequency response and the root locus analysis, and we also discuss some controller circuits. In part 2B we will dive into the calculations required for our specifications and also calculate the component values using the pole placement method, and look also at the total loop transfer function. In part C, we will verify our calculations using simulations in TINA SPICE and also MATLAB. And where necessary, we will do some fine-tuning. And this is now the topic for this video. Okay, part 2A, the theory first. If you want to use some formulas in order to get the overshoot, the settling time and also other parameters, we will most of the time use the second order system formulas. So there are the following. In this case we can look at the Y, which is our output, and the unit step input is our signal which is going up from 0 to 1 instantaneously. And the response will be then given by this formula, but this is of course not really handy to work with. So what we most of the time do is we will use this in a more compact way. So we can compact that like so. So we can make some substitutions and write it like so. And you can see here that the phi and omega d are expressed in this form. We will see that shortly how we can use that. The most important part of this graph is that we need to recognize where the peak time is, the settling time, the overshoot, and also our rise time. And there is also a band which determines that settling time. The general second order system model is given by this. This is, we have here 3 parameters. We have the DC gain, KDC. We have the natural frequency, omega n. We have also the zeta, which determines our damping ratio, which is related to the overshoot and also the settling time. So again, the natural frequency, the frequency of oscillation, so that means without any damping. The damping ratio, that is given mathematically in this form, so that is exponential decay frequency divided by the natural frequency, and that has actually no unit, so it is unitless. And the omega n has a unit of radians per second. Our DC gain, which is also called the steady state gain or steady state value, is the DC gain of our system. Okay, note that this model, what we have here, is only valid for a second order system with only poles. So that means all pole second order system. So if you have an additional pole or additional zeros or delays or any other limitations, this model will not work for that. You can still use it to have some estimate, but it can be that there are some deviations and great differences between the actual model and what you have. Okay, let's see what we can also discuss about the parameters here, because we see the peak time here. What is a peak time? The peak time is the time which you need to reach the first maximum peak of your output response. And that can be also determined by differentiating the expression for the time for our signal, which is then yt, and then equate that to 0. So you find then the moment where you have the peak. And that is given by this formula. Again, you see here the parameter we have discussed before. You see here the omega d, which is the damped radian frequency. So it's actually a pretty simple formula. You need actually the pi, which is just a constant, and omega d, and that can be determined from the natural frequency and the damping ratio zeta. The overshoot is a very important parameter. It is the amount that the waveform overshoots the steady state value. This is the steady state value, YSS. And you go above that one, and it is a percentage the overshoot, and that is given by m sub p. And this is the expression you can use to determine the overshoot, and you can use then the peak time in the formula and then have an expression that using the unit step input and also the steady state value S1, as considering that this will reach value 1, you can get that the MP will be then the formula like so. But you can also go from the given overshoot to the damping ratio, just rewrite this formula such that you have the expression for zeta in terms of the overshoot. Remember, the overshoot must be here in a scalar, not as a percentage, otherwise you will not get the correct zeta value. The rise time is the time for the waveform to go from 0% to 100%. This is most of the time used for underdamped systems. But if you have a critically damped system, then it will use, for example, between 10% and 90%. That is depending on how the waveform is. And the formula here in exact form is given by this. Again, I will leave the details out, but this is what you can use. You see here arctangent, again the zetas and omega n. But you can also use the approximated expression, which goes faster, and in most of the time for most cases good enough. That is this expression. So TR is then given by this. Again, zeta and omega n is there. The settling time is a very important parameter for your response. That's the time for the response to reach and also stay in a allowed band or allowed region. This band or this region is delta above and delta below the steady state value. So, for example, the blue line is our response. It reaches that, let's say, this safe region, but it is again leaving that region. So this is not the settling time, but this part is settling time because it reaches there and it also stays staying there. So this is the first time that we reach there. That means that's the settling time. We have two settling time criteria. Actually, there are more, but this is the most of the time used. We have the plus or minus 2% criterion. This is called indication time. There's also plus or minus the 5% criterion. This is the response time. What does it mean, the plus or minus 2% or plus or minus 5%? That means the following: the steady state value is, let's say, 1. You can go up by 2%, so 1.02, and go down by 2%, so 0.98. And for the 5%, you go 5% up and 5% down. And indication time can be calculated using the formula for our overshoot. Just equate that to 0.02 and then find the formula for the t, which is then defined as the ts with the 2% criterion. Again, this can be approximated. Most of the time people use 4 over the zeta times omega n. And the response time in a similar form. You can see here again that is equal to 0.05, and then equate that to the formula, but again approximated using the formula here, 3 over the zeta times omega n. Okay, one of the important plots we will use also in our design of the compensator for our buck converter is the loop transfer function. So in the frequency response analysis, you see here the loop transfer function. This is the Bode plot. This is the gain and this is the phase. You see here actually two parameters which we will use, which is the phase margin and the gain margin, especially the phase margin. What is a phase margin? That is maybe important to discuss that in great detail. There are stability margins, as said before, gain margin. You can find the gain margin by looking at the frequency where the loop phase is minus 180 degrees. So you look at your pink line. When you reach your minus 180 degrees, that frequency needs to be also checked at the gain plot. And that frequency is called the omega GM, so omega gain margin. And determine then the loop gain at that same frequency, that's here. And the amount that you need to go here, so the amount you need to raise your magnitude in order to get to the 0 dB, that is the gain margin. For example, you have determined this one, and this is, for example, minus 6 dB. That means you can go up by 6 dB here in order to get to 0 dB. That means your gain margin is plus 6 dB. Now, the phase margin can be determined using the frequency in the loop gain, looking here, where that is 0 dB. So you need to look at the the intersection with this horizontal axis, and you use that frequency and look down in the phase plot. This frequency is called the phase margin frequency, and that frequency will give you a phase, for example, minus 150 degrees, and between minus 150 degrees and minus 180 degrees there is a difference of 30 degrees. I just make an example here. That difference is called the phase margin. Okay, let's give an example, because that is always handy to understand that using numbers. So for example, you have a loop transfer function which is given by this. This is a third order system. You see here a pole at minus 4, minus 8 and a minus 10. Now we like to determine the phase margin and the gain margin here. So the phase margin, what we do is we just follow the procedure. You make the loop gain equal to 0 dB or equal to 1 as a scalar. That means we need to use the magnitude of this expression. Okay, the magnitude of this expression is using the formulas we know from the complex analysis of our transfer function. So that is this. You equate that to 1. You can solve this using solver, and that will give you omega is 6.79 radians per second. Now this frequency is our phase margin frequency. That is this frequency. So we go down, and now we need to use the argument or the phase expression for our loop transfer function. An argument evaluated at that phase margin frequency is then given by this expression. How can we set up this equation? You look at your loop transfer function. The numerator doesn't have any phase contribution, so that is 0. But the denominator has 3 parts. You see here the j omega plus 4, etc. And each of them will contribute negative phase because they are in the denominator. That's why you have a minus arctangent of the imaginary part divided by the real part. Don't take the j, of course, just the value itself. In a similar form for the second part and the third part. You see all of them here. But our omega pm, so our phase margin frequency, is already calculated, which is then 6.79. So when you do that, you get here minus 134 degrees. So this is then minus 134 degrees. So what is in the phase margin? Now that means how far can I go from here to the minus 180 degrees? That distance is our phase margin. So this is the formula. It will give you 46 degrees. Okay, the gain margin, and again looking at the procedure, you look first at the argument, because that is where you start with the gain margin. So you set that equal to minus 180 degrees. So you take the argument formula, you solve this, that will give you 12.33 radians per second. Now we need to use that and call this gain margin frequency, and use that in the formula of the magnitude of our loop transfer function. Now when you do that, you get here 0.3307, or in dBs minus 9.61 dB. This means we can go up by this much in order to reach the 0 dB line. So that means the GM, which is done our gain margin, is 1 over the loop transfer function, magnitude of that one, evaluated at the gain margin frequency, which is then 1 over this 0.3307, which is 3.024 or 9.61 dB. Now, looking at the simulation results, because we have done this, and this is now the plot of the loop transfer function in using MATLAB. You see here the DC gain, which is approximately 9.9 dB. You can calculate that by looking at actually this one. It should be, of course, if you look at it, if this is 0, that is 0, that is 0, you then have to divide by 1000 divided by 4 times 8 times 10. And that will give you, if you convert that to dBs, this value. We see some values here, so I have labeled them, and the script I have used is shown here. So I have defined first a Laplace parameter, and this is my loop transfer function. You see here 1000, also the 3 poles, and also use Bode as the command here to plot this body plot. Okay, I see here the first label. You see the gain margin here, which says 9.61 dB, as we have calculated. That's check. And also here the phase margin of 46 degrees, as we have calculated. You see also that the frequencies are also correct, because this is 6.79 as we have calculated, and this is here 12.3, so close to what we have calculated. So this is all checked. Okay. Now let's also now look at the root locus analysis, also a very powerful method to check the stability and also create some specific controllers for your specifications. We have here 3 plots. I will want to briefly discuss that. The root locus method is an analysis and a design for stability and entranced response, which is developed and invented by Evans 1948. And this is our engineer. And this is one of his papers, or let's say sketches or calculations, which describe this root locus analysis. And it's a very powerful method which gives you graphically what is going on and how to calculate the parameters for your controller. And this is a graphical representation set which relates the close to poles of a function as a system parameter change. So if you change your gain, you can see how your close to poles are changing, which is very powerful. And it displays the effect on the overshoot. So when you change some parameter, for example, again the gain, you can see directly how much that affects your overshoot, your settling time, your rise time, and also your peak time. Let's see that here also in this plot. So this is settling time also, so that if the settling time here will be calculated, the location of the pole here, so if I go up or down, will not have an effect, not much have an effect on the settling time. So the settling time will stay almost constant. But when you look at the peak time, if you go, for example, from this pole 1 and pole 1 location to pole 2 and pole 2, so these two poles now move to the left, your peak time will stay the same. Why? Because the omega d is the same. And the formula was for the settling time and the peak time and also the overshoot. You see here the omega d again. If that is constant, there is no change in the peak time. And if the zeta is changing, or zeta and omega n is not changing, the product is not changing, because this distance here is also called sigma d, which is this zeta times omega n. If that is not changing, again approximated, then the settling time will not change. And the overshoot, you can see that here, if you stay on this line here, that means your zeta will be constant, even though your poles are moving. That means your overshoot will not change. And you can see here the blue, the red and the pink. Each of them has exact same overshoot, but they're of course in different shape, but the MP will be the same. Okay, let's see an example, because it is, I think, much easier to follow what's going on here. This is a very general structure of a control loop. We have a gain, which is our controller in this case. We have a plant and our sensor. And our plant is given by this formula, 2 over s minus 1. And our sensor is 1 over s plus 3. So we have a first order system here and a first order system there. The plant itself is already unstable because we have a pole at the right half plane, which is at s is equal to 1. The sensor itself is stable because it has a pole at minus 3. So we like to determine here the range of stability when you change your value of the gain. So this is the k. So we'll use the root locus method, and that means we need to use a root locus equation. What does it mean? Root locus equation is 1 plus the loop transfer function is equal to 0. So that's what you need to set up. We have here the loop, that means the k times the plant, so g times h. So that's shown here. And when you now rewrite or substitute the values or the expression for the g and h here, you get this expression. And when you now further simplify this, such as you have this expression, you see here now this, and you can further simplify this. And now you have an expression that you can use to determine where the poles are not anymore at the right half plane. Because if you have a poles at the right half plane here, you will have an unstable system. So you need to have all your close to poles at the left half plane. How can we achieve that? Looking at this expression. Now, we can set, for example, minus 3 plus 2k. If that is 0, by changing a suitable value for k, then the expression here will be then s squared plus 2s is equal to 0. That means s times s plus 2 is equal to 0, and we have two poles. One of them is 0, the other one is minus 2. So both of them are in the left half plane. So there are no poles at the right half plane. So this is a condition which is stable. But how do we get to this condition? We already said that. That means we need to make minus 3 plus 2k is 0. If I make this larger than 0, I will be even better. So I will go to the left half plane so I will make it even stable. So if I now equate that and make a mathematical expression like so, minus 3 plus 2k must be equal to or larger than 0. That means k must be then equal to or larger than 1.5. So this is the minimum value for k in order to have my closed loop system stable. So if I have, for example, k is 1, I have still an unstable system. So this is the stability range. So you can go up to, for example, 25 is also fine. Still, you are stable. Okay, let's check this, and also using the simulator again, our plot from MATLAB. You see here the root locus plot. You see here the location where the poles are starting. So we have a pole at 1 where the gain is 0. That means there's no controller. And there's another pole here which is minus 3, and that is also where the gain is 0. Now, when I move on, you can see here at this location the gain is minus 1.5. The gain is 1.5, and the pole is exactly at the origin. You see here, and that is the situation where you have the pole now at the border. Now when you increase your gain, for example 2, you get actually here at the intersection. So this is again a proof that this is indeed correct. So the k must be indeed larger or equal to 1.5. And again, for this plot, you can use this script. So define first a Laplace parameter, and then g and h as given here. Make the loop transfer function, just multiply the g and h, and then do r locus, and then for this loop transfer function, and you'll get this plot, and you can then label some points. Okay. Now, the final part in the theory is about the controller circuit. We know that our buck converter is shown here because this is the buck converter we have discussed in the part 1. You see here the switch, you see here the filter and the load. Here's the load, and this is now the inductor and the capacitor with its own equivalent series resistor and also for the capacitor. Now we have discussed that in the part 1 in the open loop configuration. Now we will take our output voltage, get it to the error amplifier, and compare that to the reference voltage, and that will produce some voltage that will be then our error voltage, which will then trigger this PWM generator, and that will create a signal which goes to the gate driver, which then activates the switch, for example in a form that will then lower or increase the output voltage depending on how the output voltage is. So by changing the output voltage or by having some changes in the output voltage, you can derive this switch, make the duty cycle wider or smaller. That's the whole purpose of this feedback configuration. And this is now given in the controller diagram. So we see the error amplifier, the PWM generator, our switch, and also our filter and load. And this is the output voltage, and this is our reference voltage. And here we have our input voltage, which is our Vs. But in control theory, we only look at the parts which are changing. So that's why we have the output VO, and the input is not changing. This is V reference. What is changing is the duty cycle, and also because of that, the output of our error amplifier, which is the VC. Okay. There are several compensator or control circuits, but in power electronics we mostly use type 2 or type 3 compensated error amplifier. Type 2 compensated error amplifiers given by this. You see here an inverting amplifier configuration actually. So in the feedback you see here these components, and here you see just only R1, and this is the reference signal which will be then compared with that signal here. and that will be then our error, which will be then processed and then get to this VC, which is then this signal goes to the PWM generator. And this is the Bode plot for the gain. You see here the 0, the pole 2, and there's also a pole which is at the origin. And this line here, which is then sort of a saddle point, is given by R2 over R1. Okay, now type 3 compensated error amplifier can do more. It's also more complicated, and this is similar to that one, but you see here there's an additional R3 and C3 here in parallel with it R1. The shape is similar, but you see here that you go also up and again flatten here and then go down. So we have more poles and more zeros. Again, a pole at the origin. There are 2 zeros here, and there are additional the 2 poles. So we have in total 2 zeros, 3 poles here, and here we have 1 0, 2 poles. And the formula for the type 2 compensated error amplifier is given by this. You see here the 0 in the pole, and there is also a pole at the origin. And you see here the 0 1 0 2, the pole at the origin, the second pole, and also the third pole. Okay, now let's look at the modulator. What is a modulator? Modulators are PWM generator that needs to have a transfer function go from VC to D. Now that can be discussed using this graph. You see here our comparator or our PWM generator. We have a ramp signal which is compared with that control signal which is coming from our output. Now we have also our input, and that will then create altogether this modulating signal, which is then the signal having this duty cycle. Now you see here the ramp signal, which is then a ramp going in the standard constant fashion, but the control signal can change. For example, if it stays here, it can go up because we need some more output voltage or less output voltage depending on what's going on. Then the duty cycle will change. For example, here the duty cycle stays the same, let's say 25%, and then I need to go up by the control signal. That means if this is going up, then the duty cycle will also increase, so I need to increase my output voltage. And that is actually described here. But we need to have a mathematical expression for that. So the modulator average output voltage is given by this integral. We have seen that also in the previous examples about how to calculate the average value of a signal. So the modulator output voltage given in time domain can be averaged using this formula. And you can have then only the part where you have the input from Vs. The modulator transfer function, which is called Ms, given here in the generic form as in the Laplace parameter, is a delta V modulation over the delta control signal. Now we can look at it in more detail by using the derivative, so the derivative of this signal, and when you write it down in more detail, you can see that the modulation signal or modulation voltage can be also written like so. And now you see here that we can cancel out the control signal here and the control signal there, and then that will give us Vs over V ramp. And that is a very simple formula which is not dependent on the frequency. I have said that of course before, but it's just given here generic form. You see that you need your input voltage and also your ramp voltage, ramp amplitude. So if your ramp amplitude is, let's say, 5 volts and your input is 20, that means 20 over 5. That means you have here a gain for your PWM generator of 4, and that is important. Okay, the filter and the load, which is this part, will also have its own transfer function. Now that can be done using the analysis in the AC domain, so you consider this as the input and that one is the output. So it is then VO over VD, which is then the voltage across the diode here. Now that can be calculated and then determined. This is the result. I see here a second order expression. We have a 0, 1, 0 and 2 poles for this filter and load transfer function. The compensator itself can be again type 2 or type 3. Now the compensator transfer function G is then the VC over VO. And not Vref, because Vref is a constant, so we only look at the changing parts of our diagram. And that is given by the open loop transfer function of our error amplifier divided by 1 plus the open loop transfer function of our error amplifier times the feedback element beta. But beta is most of the time the part which is as a passive network around this op-amp. If the op-amp has a large loop gain, we can almost approximate this by 1 over beta, but I will come back to that shortly. So the error amplifier open loop transfer function is given by this. This is generic first order transfer function for the error amplifier. You can also see that in op-amp theory. You see the DC voltage gain and also a pole, one pole at omega PE. So this is the error amplifier pole. And as said before, if the loop transfer function, so that means the open loop transfer function times the beta is much larger than 1, so that means much larger than this one, this can be approximated by like so, and that goes to in 1 over beta. And that is most of the time used if you don't need that much accuracy in your results. And the feedback transfer function or the feedback element is then given by this beta. So we will use 1 over beta, and that will speed up the process and also get the results much easier. Okay, now the part 2b about the calculations. Now we know we have the specification like so. So we said that we need a DC input voltage, 60 volts, average output current, and also the maximum percentage peak output ripple. Now we have done this in part 1 as said before in the open loop configuration. Now in part 1 we did this. So we came up to the inductor value, the capacitor value. There was also the capacitor equivalent series resistor of 400 milliohms. So that was also taken into account. This was not taken into account, so this is now here new. So I just put here some convenient value for the inductor, which is most of the time seen. I just want to make it more realistic. And we know that our load was 7.5 ohms and our switching frequency was selected as 100 kilohertz. This is all from part 1 of the video. Now the buck controller, so the buck controller itself, IC, I have chosen for the LM5146. And that is the following. You see here the chip with some inputs you can use in order to create your controller. You see here the capacitors C1, C2, and also resistors R1, R2, and R3, and also R4. And this is the compensator, the type 3 compensator we actually have seen before. And that needs to be connected in this form, so the great details are given in the datasheet of this buck controller IC. You see also the output here, the input, and also our inductor and the capacitor, which you need to put here. So our inductor will be then 300 microhenries. Here our capacitor, which is then 20 microfarad. This is just the input filter capacitor, which needs to be put here to get rid of some ripples if necessary. And there are also other components and also other IOs here to make the IC function, also get some features like sync in, sync out. But this is all left as a detail besides this video, because you can see more details in the datasheet. I'm only focusing on the configuration of this buck controller IC and where you need to connect your components in order to have your controller in a feedback configuration. The input voltage range of this IC I've actually searched around which can be used for our case, because we have 60 volts input, and this has an input range of from 5.5 volts to 100 volts, so this is fine. It can produce a maximum output current of 20 amps, so that is way above what we need. And there is a control mode here, which is voltage mode, so the way it controls the buck controller, the buck converter action, is by using voltage mode. There is also another mode which is called the current mode, and the operating temperature here is between minus 40 degrees and 125 degrees. Okay, the reference voltage here is important. That is given from the datasheet, is 0.8. I will show you just a part of it shortly from the datasheet. The ramp amplitude from the PWM generator can be calculated using this formula, so it depends on your input voltage, and over 15, that means in our case will be then 60 over 15 will be 4 volts. And our error amplifier open loop DC voltage gain, that is again from the datasheet, which is 94 dB and given here as a scalar value. and the gain bandwidth product from the datasheet was 6.5 megahertz, but you can now use the open loop DC voltage gain and the gain bandwidth product to calculate the error amplifier open loop compensator or compensation pole by knowing that the gain bandwidth product is the open loop DC voltage gain times the pole will give you 6.5 megahertz. So that will be then here approximately 130 hertz if you don't calculate this. Here is the part of the datasheet from this buck controller IC. You see the PWM control here. You see some duty cycle maximum for some specific switching frequencies. Here you see the gain KFF, which is the PWM feed forward gain, given as V in over V ramp, and we have used this formula. We have also discussed how we get to this formula. So it is the Vs in our case, not V in, over the V ramp, and that is typically the gain is 15, and it is only valid between 6 volts and 100 volts as the input voltage. So the gain is always 15 for our PWM generator, but you need to know what your ramp signal is, so that can be determined looking at your input voltage. In our case it is 60 divided by 15, so it will be 4 volts. Another one is the reference voltage here, which is 800 millivolts. Typically it can be 1% down and 1% up, and that's why we have here 0.8. You also see here the open loop DC voltage gain 94 dB, and also the gain bandwidth product or unity gain bandwidth 6.5 megahertz. This is all from the datasheet of this buck controller IC. Another important plot from the datasheet is our efficiency. So this is the efficiency here, and this is the output current, and it is plotted for several input voltages. So going from, let's say, from 15 in black, the red one is 24, this one gray one is the 36, etc. We have as our input 60 volts. That is actually this, the second one. So almost dark green, and we know that our output current must be 2 amps. Okay. If I now make the intersection here between the 2 amp and also this graph, I see here an efficiency of 92%. We haven't taken into account the efficiency in the part 1 of our discussion. So if we know that we also need to take this into account, we need to maybe create more duty cycle or change the ratings of our components to get the 100% F in the practical sense. So there might be some deviations in the actual circuit, but it is still pretty high. So now let's collect here the parts here, and this is now again the switch, the filter and load, and now our compensating network. You see here the type 3 compensating network. This voltage here will be taken here, and then using the voltage division by R1 and R4, put here in the inverting input of our error amplifier, and will be compared to that reference voltage, which is 0.8 volts according to this buck controller IC. And that will then go here, the error voltage in this PWM generator, compared to that ramp signal, and then will be then activate this driver to change the duty cycle for this switch. That's the whole actually idea of this diagram. Now the compensator values, we now actually reaching are one of the important parts, and we will for that use the pole placement method. Now how do we do that? Now we have chosen for type 3 compensated error amplifier, and for that the transfer function is like so, and that is given in a more detailed form like so, because we have here 2 zeros and 3 poles, but now you'll see that also in the components values, so in the expressions, and this can be most cases approximated, and it speeds up again the process of calculations, because most of the time the R1 is much larger than R3, and the C2 here is also much larger than most of the time than C1. That means the following are transfer functions. Since R1 is much larger than R3, this is just R1 as approximated. That means R1 over R1 times R3 times times C1. That will just give you 1 over R3 times C1. In here, this is only part which then the R1 is dominating, and here you see that the C1 and the C2 is there, and C1 and C2 is again there, and that part is then Again, since C2 is there dominating, it means C2 over C1 times C2 times R2. That means 1 over C1 times R2. That will then end up to this expression. You see here again what I just described. This part is going to 1 over R3 times C1, since the R1 is much larger than R3. And here you only leave the R1 because that is larger. This is unchanged, this is unchanged. Here, since C1 is much smaller, or C2 is much larger than C1, that will be given then C2 over C1 over C2 over R2. That is then approximated 1 over R2 times C1. Now, why is this better or faster in the calculations? Now you see in each part, 0 here, 0 there, pole there, pole there, that you can calculate the specific poles and the zeros using only 2 component values. Here you need to use 3 component values. So this is the reason for making that. Now let's first go to the step 1, which is about the resistor divider values. I said already in the output voltage here, we need to divide that using R1 and R4, and that apply that to the inverting part of our error amplifier, having the compensation network. So that needs to be compared to the reference voltage of 0.8. That means the following: the reference voltage, which is also this non-inverting part, in order to have that exact same, so we compare that, must be R4 over R1 plus R4 times the output voltage. But we can select a value for R4, for example 10 kilo ohms, then we can rewrite the R1 in this form. That will be then VO over Vref minus 1 quantity times R4. Now we know it is 15, so that's our output, because we needed that. We know that our reference voltage must be 0.8 and then minus 1 and then times 10 to the power 4 for 10 kilo ohms. We get now 177.5 kilo ohms. So we already have one of the components calculated using the one selected value here for R4. So we know the R1 and R4 already. Okay, step 2 is about the resonant frequency of the filter, which is from here. That is determined, again, just ignoring the RL and RC here, which is our series equivalent resistor for the inductor and also for the capacitor, given by this expression for the resonant frequency. Now, when you now substitute this 300 microhenries, also 20 microfarads here, they will give you 2055 hertz. Now the first zero frequency, which is this 1 over R1 times C3, that can be set, because this is about the pole placement method, we can take that a little bit slightly smaller than the resonant frequency we just calculated. So that can be then, for example, 90% or 95%. It doesn't really matter, just slightly smaller. So I just take it 90% of the resonant frequency here. So that means the 0,1 frequency is 0.9 times the resonant frequency. So it means it will be then 1850 hertz. And we know the 0,1 frequency here is then 1 over 2 pi R1 C3. We know R1. We know what we have here for our first zero frequency, so we can calculate C3 here. Just rewrite this and substitute the value for the R1 and also what we have for our first zero frequency. That will give you C3 of 484.7 picofarads. Okay, that's also calculated. Now let's bring here and then create some space to calculate the next part, which is the second pole frequency, because the first pole frequency is 0, we know that, because it's at 0 hertz or 0 radians per second, and second pole frequency is 1 over R3 C3 in radians per second. Now, we need to first select the crossover frequency, which is also called the unity gain frequency. Now in this case, I have taken that as 10 kilohertz, which is 10% of the switching frequency. So it is 1 decade below the switching frequency, at least one decade below. You can also take here as 6 kilohertz or 8 kilohertz, it's you if you prefer, but we don't want to have much gain at our resonant as our switching frequency, because that will create a lot of distortion. So that is why we have a little bit smaller, in order to reduce the gain at that frequency. So that means in order to set then the second pole frequency to the crossover frequency or unity gain frequency, we say fp2 is then equal to f unity gain frequency is 10 kilohertz. We already said this is the formula for our fp2, so that means the R3 can be calculated since we know the C3 and we have selected our second pole frequency. And that will give you now 32.84 kilo ohms. Okay. Step 5 is we need to now look at how much compensator gain we need in order to get at the crossover frequency we have selected. Because there's a gain which might be not 0 dB or 1, so we need to compensate that. Now, the modulator gain, we already know that is 15, so 60 over 4, that is given in dB is 23.52 dB. We know that we have a filter, which is given in the Laplace domain like so, and that can be then given here in the j omega domain by just converting this s to j omega. Now, when you now take the absolute value, so the magnitude of this one, that will be then this expression. Now, we need to know what the value of this expression is at our unity gain frequency or a crossover frequency. So that means the omega t, which is then 2 pi times ft, so 2 pi times 10,000, will be then evaluated here in this formula using the RCC, etc., all the values we have for our circuit. Now that will give you 0.04636. Now the loop transfer function or loop gain at that unity gain frequency must be 1, as said before, or 0 dB. So that means we need to see how much we require as a compensator gain to get this 1. Now the compensator gain times the modulator gain times the gain of the filter with a filter and a load at that unity gain frequency must be equal to 0. That means the compensator gain is then 1 over the product of the modulator gain and the filter gain at, again, the unity gain frequency. Now we know 1 over 15 times this 0.04636, and that will give you 1.438. So our gain, compensator gain, required in order to lift that to 0 dB or 1 is this much, so 1.438 or 3.155 dB. You can also get to this value by looking at these two values that needs to be add up to 0 dB, so that's also possible, and you get also this value. Okay, so we know our required compensator gain to get to the unity gain for our loop gain at the crossover frequency, also called unity gain frequency. Okay, now the compensator gain setting. Now we need to use this K compensator in order to calculate the other component values, because we know what the compensator gain is at the crossover frequency. That is given by R2 over the parallel combination of R1 and R3, sort of the inverting amplifier formula. That's actually shown here. And we know the K compensator, we know already R1 and also here an R3, so we need to calculate R2. And that's the parallel combination, so we need to use the parallel formula. So that means R2 is then given by this expression. Just rewrite this formula. We need to have the parallel combination of R1 and R3. That can be then like so. So use this K compensator and also the value for the R1 and R3 here. And that will give you for R2 39.85 kilo ohms. So we're getting closer and closer, so almost all the components are calculated. Now the second zero frequency, that is this part, 1 over R2 times C2. Because we know R2, we can calculate now the C2. That is the next step. So that will be taking slightly smaller again than the resonant frequency, similar actually to the first zero. So the second and the first zero are exact same in frequency, but there will be of course different values for the components. Again, 0.9 times the 2055, so again 1850 Hertz. But now we will use this formula and now calculate the C2 using the R2 and the second zero frequency. That will give you now the capacitor C2, which is then 2.159 nanofarads. Okay, now the next one is our third pole frequency, which is the final one, and it will be taking about 1 decade above the unity gain frequency or the crossover frequency. So that means 10 times the 10 kilohertz, that means 100 kilohertz. Okay, now the FP2, which is the pole frequency here, it's then given by this, so we can calculate C1 using this expression, and that will give you 39.94 picofarads. What you recognize is the following: we had made an assumption to get to this type 3 compensated error amplifier. We said that C2 is most cases much larger than C1, which is true. You see here this is 2.159 nanofarads, which is much larger than this one. We also said that R1 is much larger than R3, which is in this case not much larger, but it is at least, let's say, 5 times larger, so that is also fine for all practical purposes, and again to speed up the process of the calculations. So again, a check. Okay, total loop transfer function can be then determined like so. So the loop transfer function L, which has nothing to do with this inductor, is the modulator gain transfer function times the filter and load transfer function times the G3, which is called the type 3 compensated error amplifier transfer function. And that is in total this one. So I've now color coded that: red for the M, the blue for the F, and the pink for the G3. So you see this is actually a pretty, let's say, wide formula. We are not going to use it here, but I just want to show you that this is the actual formula for the loop transfer function. You need to use that in MATLAB to plot and also create the plots for phase margin, etc. Now these are the values which then can be put in here and then have an expression for the loop transfer function. Okay, now the part to see about the simulations. First we'll start a MATLAB Simulink, and again we need to use that loop transfer function just presented. Okay, this is the script I have prepared. You see again the definition of the Laplace parameter, the specifications, the selections. I just made the switching frequency of 100 kilohertz. The buck converter IC we have chosen. You see the reference, the ramp, and also the DC open loop voltage gain, and also the pole for the error amplifier at open loop configuration, and also other parameters all shown here. So we need to look at the script maybe in briefly. The transfer functions here for the modulator, you can see that here, M Vs over V ramp, so that is the modulator transfer function. The filter and the load, that is shown here. Let me find it here. This is the F. So you see here the filter and load transfer function, which is this one. And for the compensator G, I called here G, which is actually G3, which is called here G compensator. And now it is also taking into account the part of the error amplifier, the DC voltage gain, and also the error amplifier compensation pole. That's actually shown here. Okay. So all together, loop transfer function, again a modulator, the filter, and also G3. Again, this must be G. So I have changed that here. You see that this is G3. Okay. Now let's look at the simulations for the loop transfer function in MATLAB. You see here, this is now the loop transfer function of the filter and the load only. Well, you see that this is the DC gain is 0 dB. Is actually logical, because if we're at DC, the inductor is short, so that means only RL, and the capacitor is open, so this is just R over RL over R, so that is just let's say a very small error, so that is just 0 dB. That's actually pretty easy to find. There's also a peak value, so there's a peaking here, gain peaking. But let's see what we need to have. This is the expression for the filter, again with the load in the j omega domain, and this is the expression for the gain. And we know if we evaluate that at the unity gain frequency, which is at 10 kilohertz, or 2 pi times the 10 kilohertz, that will give you this minus 26.7 dB, which is actually what we see here. So that is actually pretty fine. Okay, and about the argument, which is our phase, you can calculate that using this expression. One thing we need to note is the following. The numerator will give you some phase contribution by arctangent of the imaginary divided by the real, which is just divided by 1. But the denominator has the following expression, again a minus sign, so you take the imaginary divided by the real, which is this, but the real part is negative. That means you need to here also add a 180 degrees. That is the reason for having this 180 degrees. Otherwise, the formula will give you the wrong answer if you don't take this 180 degrees into account. Now, when you do that, you get now here minus 146 degrees, if you just use the values here. And if I look at my loop transfer function, I see indeed at this 10 kilohertz minus 146 degrees. So again, proof that this calculation is correct. Another part is the phase margin, an important parameter. We have discussed that in the theory part. We see here it is a little bit over 58 degrees, so that is perfectly fine. And we see also our calculations are correct. Okay, next is the loop transfer function of the filter and also including the modulator. So the PWM generator will only add a gain, so there is no phase addition or subtraction. So that means it will stay the same shape, so it will go a little bit up or some up, so it will be shifted in the positive direction. And you see again the part here, so just G now time is the M times F, so the transfer function of the modulator and the filter. You see here again the part where you have the 10 kilohertz. Now you see here it is shifted by minus 3.16 dB, and if you remember, we need to add this plus 3.15 dB or 3.155 dB for a compensator gain in order to get again to the 0 dB. That's the reason. That's also what you see here. And we also see at the same frequency that the phase is again minus 146 degrees, so that hasn't changed because of this PWM generator. But the phase margin has changed. You see that the phase margin has changed. It was before 58, now it is almost 32, so it has decreased drastically. That is really because of this gain, so it is shifted up. So, okay. Now, looking now at the loop transfer function of the compensator only, so this is the compensator network, this is the type 3 compensating error amplifier. You see here the part where you have the 10 kilohertz again, a small gain of 0.18 dB, and there is also at the same frequency a phase contribution of 20 degree. So that means actually the following: our error amplifier will supply or provide a phase of 20 degrees at that chosen unity gain frequency or crossover frequency. It is not exactly the crossover frequency as you can see here, because the crossover frequency will make the magnitude here 0 dB, but it's close. So it is a little bit larger here. So it maybe I need to go a little bit to the left, so that might be maybe 9.8 or 9.5 kilohertz instead of 10 kilohertz. Okay. Now looking at the loop transfer function of the filter, the modulator and the compensator all together. So we make now the full loop circle. That's shown here, so the G loop. What do you see? Now again, we look at the labels here. We see the phase margin here. It has now increased from 31.5 degrees before now to 54. Still a little bit small than before. It was before 58 in the first case, but it's still good enough. So there's not much a difference compared to the first case. And also the unity gain frequency or the crossover frequency is not anymore 10 kilohertz, but let's say 7.9 kilohertz. So I go down, or we go down by 2.1 kilohertz. So that is perfectly possible because we also made some approximation in our calculations by assuming that some values were larger than the others. Let's say we said R1 is much larger than R3, which is not true because not much larger. It is larger, but not a lot larger. So there are some errors we also have made before we started the calculations. Okay, so the phase margin is 54 degrees. It is sufficient phase margin, so that will create definitely a nice step response and make this loop stable. Now, going to the final part of the simulation, then using now the Tina TI SPICE. Okay, now again, we look at the simulator circuits. This is the filter only in Tina TI SPICE. You see here the input AC voltage just to generate this Bode plots. RL, L, RC just the equivalent series or the non-ideal effects in our inductor and the capacitor, and also our load of 7.5 ohms. This is the filter and the modulator itself. You see here what we have used. We have used here a voltage controlled voltage source. In this case we had the PWM generator, so our modulator has a gain of 15, so this is just this value. So the only change here between this one and that one is just this addition of gain of 15, so voltage gain of 15. This is the compensator. You see here the compensator in a model where you have the error amplifier as the first order model of an operational amplifier. Use the operational amplifier in, which has a DC open loop voltage gain of, well, it was 94 dB, which was then reflected in the as a scalar value 50,118. So that's actually what you see here. There was also a compensating pole in the op-amp, which was 130 hertz. Approximately that is now done by this RC element. So you do 1 over 2 pi times the product of these two, you get approximately to that 130 hertz. That's just to make it more accurate. And this next stage is about the phase inversion, because we have an inverting amplifier. So that's why we have it here. That goes to the output. Now, between the op-amp in here and op-amp out, that's actually here, in between there you have the R2 and the C2, that is this one. And then on parallel to that one we have C1. And in the front we have the R1 and R4 here, that is the division here to grade that from the output voltage. You also have here the R3 and the C3 here, that is the series combination across R1. So everything is actually as given here in a different form redrawn here. And the full part, including the modulator and also the output filter or our buck converter model, is shown here. And this is now the filter, the modulator and the compensator all together. Okay, we will use this circuit to evaluate the phase margin and also other parameters. Again, our amplifier had the open loop DC gain of 94, and also the open loop compensating pole was approximately 130 Hz. Again, for that we use this part of the circuit. Okay, break now all here, and now let's start at the loop transfer function of the filter only. That's shown here. So what you see is that there's a almost 0 dB, so that is in agreement with the MATLAB Simulink, MATLAB simulations. We see here at 10 kilohertz minus 26.7 dB, also the same as we had seen in the MATLAB. And there is also a phase of minus 146 degrees at 10 kilohertz also. So that's also what we have seen in MATLAB. So this is all in agreement. Now looking at the loop transfer function of the filter and the modulator, so just the gain. So what you see is that indeed the gain at low frequency goes up. There's also a resonant frequency, again what we had before. So that's also at the same frequency. But now you see indeed that the gain is not anymore what we had before, but now it is minus 3.155 dB. This is indeed how much we need to increase, so the positive of this one, to get this at the 0 dB. And this is again the same phase, so the phase will not be affected by a change in the gain. Of course the phase margin will be affected, but not the phase at that frequency. Okay. Great. Now the next one is about the loop transfer function of the compensator only. So this is the compensator. We have designed, you see the crossover frequency is not 10 kilohertz but 9.5 something, so it is some error of 470 hertz. It's perfectly fine again because we made some approximations here. And there's a phase of 200 degrees, but it means 160 degrees. So that means from looking minus 108 degrees going up, we create actually a positive phase contribution of 20 degrees. Again, in agreement we have seen in MATLAB at the same frequency. Okay. Now, looking at the full plot, full loop, which is the filter, the modulator and the compensator, that's all shown here. Now again, all the elements will have an interaction with each other. So the compensator alone was there, it was almost 9.5 kilohertz, the crossover frequency. Now we get all the elements together in one big loop, Now the crossover frequency is even lower, so it is almost now 7.9 kHz. So I have an error of 2.1 kHz. Is this a problem? Probably not. This is of course also just taking randomly, but if this is a very specific value you need to create, maybe we need to tune. In this case, this is not necessary. I also see that the phase here is 53.6 degrees, and that's at the same frequency. What does it mean actually? The following is happening in the SPICE simulators. There's a sine inversion here, but still this part is considered to be a phase margin itself. So we have a phase margin here of 53.6 degrees. So that is an agreement. With MATLAB we had here almost 54 degrees. Alright, this concludes our second part. We have now discussed the complete loop transfer function for our buck converter and open loop, and we have created or designed our compensated network and also calculated the component values here. The summary is shown here, so all the values are shown here. We also have chosen a buck controller IC in order to create this feedback loop here. If you have any questions about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.